Okay, so we've managed to design our beams. So the next thing is we need to design our columns. Now, what I'm simply going to do is I'm going to select all my columns in the module, select by material type, member type. Then I'm going to open this in a new window. I'm going to display my bending moment diagrams and my axial force diagrams. Now remember, columns usually are subjected to axial force, so you want to check the Fx force. This is the one that you should be interested in. You can as well try to check your bending moment diagrams, and on the load you make sure that you are on ultimate limit states. Now you can see that the column that is heavily loaded in our model is this one here that has got 759.01 as our axial load. So for now, for this example, we are simply going to design this column. Now you can categorize your columns depending on the range of the bending moment diagram in which they fall. You might have at least you might have 3 or 4 categories of columns classified according to the bending moment, according to the axial force they are carrying. But for now, I'm simply going to design one column to demonstrate how it's done. So let's select our column, which is this one, um, and then we'll go to design of provided reinforcement of RC elements. Again, here we choose manual combinations. Okay. So now, like we did for beams, we need to assign our parameters, calculation options. All these are pretty much straightforward. Optimization level high, this is fine. I might want to fix my cover, which is okay. Longitudinal, then concrete C30 is fine. That's what I want to use. The longitudinal reinforcement, I want to use Y16 transverse reinforcement. I want to use R10 for my stirrups. I can always save this. Okay, that's it for that. Then we can move on to reinforcement patterns. Try and play around with the settings. Nothing much to change here. Everything seems pretty much okay. I would love to leave this one checked. I would love to leave these ones as they are. Shapes, it's fine. I can save this as BMG column. Okay, I think that is it for the column. Nothing complicated. Let's calculate, see what we are going to get. So cover does not satisfy the given. Okay, so let's go back and check our parameters for the cover. We can try and make this 25, see if it's going to make a difference. We recalculate. Again, we have the same issue. We can okay, let's leave it at 30. And then let's try to use less tube. Okay, so the issue that we were having there is that the cover was too much for the steel. The Y16, because it's large, it's too large. The spacing between the bars was too little considering the column size that we're using. That's why the software was refusing. It's giving us that warning. But now when I switch to white wolf, you can see clearly that now we have our reinforcement done. The column is designed. And one thing to take note of is at the bottom where there's high bond bending moments, you have the stirrups being uh, you have the spacing here being way less because you need more stirrups than where you have less bending moments on top. And you can always check your results and see the axial force 759 is okay because we're using the ultimate limit state. Then you can also check your factors of safety. We have 1.21, which is okay, 1.49, showing that the applied load is over the design capacity over the applied load is more than 1, which is okay. Yeah, I think this is pretty much it. You might want to change your steel because I know most of your columns, depending on why you're submitting your drawings with the council, they might insist that you use Y16. So let's try and just see how we can revert back to Y16 without having any issues. So let's try and see that warning we were getting the first time. Okay. Oh, seems we're now fine with Y16. Yeah. So uh, basically this is it as far as column design is concerned. Then you can always look at your note and see how the software is calculating the reinforcement, the factors of safety involved, and everything else. And then you can come here and you'll as well check your drawings. It's going to show you the spacing of the stirrups. It's going to show you everything else you need to see. However, these drawings, like I said, for the beam, they're not so good. So you might have to export these drawings to Revit to create proper drawings for the contractor. Now, one more thing we need to do is we need to design our foundation. We've designed our column. Let's design our foundation. Like I said, for the columns, even for the foundations, you can always categorize them depending on the amount of load they're carrying. So for now, we are simply going to design one of them just to demonstrate how it's done. Then you can always design the rest at your own time. Okay. Again, when I look at my plan here, let's try and see how we can. When I go to my base here, I see that this is the foundation that's carrying the heaviest load. And what I would simply do to design it, I'll simply select it to make sure it's highlighted. And then I'll come here and design, provide the reinforcement of RC elements. Now, for foundations, this is something that you should take note of. When you're designing foundations, we don't use ultimate limit state forces. We use simple cases, which is service loads. So please, when you're designing foundations, always remember not to check the manual combinations, but to use simple cases, to use service loads. Otherwise, as far as I know, working with robot, if you try to use manual combinations for foundations, it simply won't work. It won't give you the proper results. But if you use simple cases, you're going to get the results you need. So let's go to simple cases. Now, if you cannot see your element after selecting it, it simply brings this window and says no selection. You can go to your reinforcement elements here, RC component inspector, and then you select your foundation. Simply it's going to pop up. And then very quickly, let's assign our design parameters for our foundation to our footing. I would simply maintain the rectangular shape, which is what we are doing now. This is for architect. This is a simple strip footing for architect, so we're not really doing that now. We are mostly concerned with the structural footing. Now, these ones, EX and EY, you can see here they're shown what they relate to. This is the offset, so we want to make it 0 so that our column is centered on the foundation. B and A, these are automatically calculated from the column, so this is the size of the column, and these you don't have to change them, you leave them the way they are. And then the heights, H4, this is the height of the binding concrete, which is usually 50 millimeters, so this is fine, 0.05. And then H2, the height of the stub column. Here the software will give you a warning if you use 1.1, but I like using that because it more accurately depicts the height of the stub column, which is usually 1.1 meters below the slab level. And H1, this is the depth of your footing. You can see H1 here. This one you can assign it as, I like to use 0.4, and I like to fix it. And then A and B, you can leave these as they are and make sure they're not fixed, so that the software will calculate the size of the footing based on the bearing capacity that you're going to assign. And then you can go ahead and apply these settings. Now, before you calculate, you need to check your calculation options again. Here, our cover is 50, we are okay. Not much of a problem. Seismic, we don't have anything to do with this for now because this relates to earthquake activities and all that. So right now we are not really designing for earthquake situations and all that. So concrete, let's use C30 for foundations, and then longitudinal reinforcement, let's use Y16. Transverse reinforcement, let's use Y16 as well. And then additional reinforcement, we can use R12. You can save this as something BMG14. Save that. Okay. Now for foundations, before we go on to the geotech, let's go to the footing parameters, how it's going to arrange reinforcement. When you go to advanced here, top reinforcement, say yes, so that it will always put top reinforcement. You can say automatic, where it only puts if it is required, but in this case, let's say yes. And reinforcement pattern, you can check this, which is what I like to use. And okay, let's use the bottom one. I think this is fine. And then this one, I like to use the bottom one. It's simplified. This is fine. To use the bottom one, then our bars. Connecting to column, yes. Okay. Shapes, this is to do with the bar bending schedule. Hooks only if necessary. Let me try and check this, see what happens. Then I'll save this as BMG footing pattern. Okay, so we are almost done, but there's one more step. You need to assign your bearing capacity, the bearing capacity of the cell. And there's one more thing that I need to mention. Let's simply go to the geodetic options. For foundations, if you check our structure, we designed our connection as pinned. This is usually what is done because if you assign fixed connections to your foundations, they're going to have moments and they're going to be more expensive to design. But when they're pinned, they are not carrying any moments. So that's something you should keep in mind. We use pinned connections most of the time, unless otherwise. But for foundations, we use pinned connections. Now, under stress here, make sure you set your bearing capacity in megapascal. Let's assume we are using 150 kilopascal, which is 0.15 megapascal. I'm simply going to say okay. And then once that is done, I'm going to calculate. Okay. There's an issue with the reinforcement, foundation results. It's going to show you your axial force, your moments, and you see the moments are very little because we assume our connection is pinned. That's why our moments are not so high, but our axial force is high, so that's what the critical governing case is. And the reinforcement for our foundation is done here. You can see it's putting Y16 top and bottom. And one more thing is you need to check the size it has used. So after calculating, it has given us the size, the width, and the length of 2.3, which is not so bad considering the amount of load that the column is carrying. So this is fine. Yeah, I think this is pretty much it. Let's just go back to our calculations and check the error. So it's saying factor of safety. There's an issue with the factor of safety. So what I would want to do in this case is I might want to go back and try and play around with the height and apply this. Let's try to recalculate. Again, we have the same issue. Okay, let's revert back to 0.4. And so next thing I want to try is to change the steel reinforcement size to Y20. Okay, let's see if we are going to have a similar issue. Top reinforcement in direction of Y-axis. Okay. Foundation reinforcement. Okay, let's go back to our settings. Let's try putting this on auto. Let's recalculate. Okay, so now we are fine. The errors have all vanished, but now we have disabled the top reinforcement, so we're now good. Let's try use this another pattern. Okay, let's try use this pattern. For some reason, I think I like to have the top reinforcement, but there could be some detailing constraints. That's why the software is not so happy with the idea of putting the top reinforcement. It's giving us that error. So in any case, I think this is it. Then if you want to check your note, how the software is calculating your forces and all, you can check them here, and you can also check your drawings.